Welcome, everyone. We're really, truly excited to have you here for week 6. Gosh, it's week 6 of the Australian Virtual Astronaut Challenge. So very excited to have you here. It's been a bit of a journey, hasn't it? We've been through the ISTAM process and hey, week 6 is all about communication and really love you being here. So if you are joining us, please feel free to scan that AHA QR code because, hey, you get to do something today. Definitely so. But before we get going, my name's Ben Newsome, and I do want to acknowledge that I'm hanging out with you in Western Sydney on the lands of the Darug people. Thank you so much for having us. And I want to acknowledge all the traditional custodians of the variety of lands that we're meeting on. And honestly, it's not just in Sydney, it's right across Australia and over the side of the other globe. And I want to say, pay respects to all our elders, past, present, and emerging, and extend that respect completely to all the Indigenous people who are joining us today. We are going to have a fantastic day. So if we may, I'd love to have a look at our the people who are joining us through the this particular session. Another jam-packed session, I must say. There are a lot of people involved. And Dr. Scott Sleap, the person who really has helped pull us all together. Scott, how are you doing today?
I'm having a fantastic day from Wanneroo land here in the Hunter Valley. And once again, just really excited about the quality of the work we've got today and the people we've got speaking to you. So over to you, Ben.
Hey, much appreciated. That's from Scott from STEM Industry School Partnerships, and someone who could not be, we feel like it'd be amiss if we didn't say hi to Ted Tagami from magnitude.io. How are you, Ted?
Fantastic, Ben. Good morning to you. Good afternoon from Berkeley, California, home of the Ohlone people. Really looking forward to the communication segment. The 6 weeks has been absolutely amazing. I'm really looking forward to week 7. I wish there was a week 7, right? Back to you, Ben.
Absolutely, Ted. And very much someone who's heavily involved, and not just in the States, we'll get to do all sorts of cool stuff. Laurie Waters from Magnitude as well. Laurie, how are you?
Wonderful. Thank you. I'm coming from Florida in the United States of America. And just last night, we saw another Crew Dragon launch. So we get to be the home of the rocket launches near Kennedy Space Center.
I'm so excited that rockets are launching from the Kennedy Space Center with people on them. It is so very cool. Now, someone who definitely gets to see this quite a lot is Jim Christensen from the Aldrin Family Foundation. Jim, how are you?
Ben, good morning. It's great to be with you. Yes, we launched another one, and I live about 10, 12 miles from the launch pad, but I am right in the middle of the United States today. I'm in Ames, Iowa, with being a grandparent. So I didn't get to see the launch last night. Lori had to take care of that for us. Back to you.
Mate, very jealous, I've got to say. Now, that's also jealous also of what Carey Furze gets to do in terms of helping people with literacy, as well as doing some STEAM stuff. Very interesting. Carey, welcome to the Australian Virtual Astronaut Challenge.
Hi, Ben. Thanks for that. I'm coming from Sydney. I feel like it's a bit boring after the others. And I am on the traditional lands of the Cadigal people. So thank you for hosting today.
Carey, not at all. I actually get to see where you get to see your view. It is not a viewing view as you look over Gadigal people's lands. It's really cool in the heart of Sydney. Very neat. And someone who's not in the heart of Sydney, up in North Queensland, is Wendy Bode. Wendy, how are you?
Oh, I'm good, thanks, Ben. Good morning, everyone. So I'm from the Queensland Virtual STEM Academy in Townsville, North Queensland, and we are in the Wulgarukba and Bendel people land. So I'm really excited to see the pictures that the students are going to provide for us.
Oh, absolutely. And they're going to start coming in thick and fast because we have a couple of hundred schools. That's true. And and we get to maybe just shape that a little bit today about the communication of this. Thanks so much, Wendy. And down south, as always, is Ian Preston. How are you doing today?
Yeah, doing well, Ben. Thank you. Welcome, everybody. Coming to you from Griffith in the Riverina, Murrumbidgee Regional High School, home of the New South Wales Virtual STEM Academy, and I'm on Wiradjuri land. So looking forward to today's activities, and it's been a great 6 weeks.
Fantastic. All right. So that is our panel today, and remember, you do get to do something using those AHA slides, so be ready for that for sure. Now, I thought I might give you a heads up. Some of you teachers know, but maybe you all don't know quite yet. But you know this work you've been doing on the Australian Virtual Astronaut Challenge? Guess what? You can repurpose that same thing, that same 1 minute pitch that you're doing to Ted Tagami and Laurie from Magnitude. There is an Australian Space Biology Symposium coming up. Seriously. So I want to quickly just show this for you. Did you know that we can submit what you've been doing throughout this whole 6-week challenge? There is a competition, actually there's several competitions that you can, well, put your information in and repurpose the stuff. So in the chat is a link, it'll pop in very soon. And it also teachers, please check your emails about this too. This is something where you can submit to a genuine, real research, engineering, education opportunity where all sorts of spacefaring nations are descending on Australia for a major symposium, the Australian Space Biology and Health Summit. It's going to be very, very cool. I just thought I might just throw that out there. Now, this is a jam-packed session, so I want to kick it off by handing over to Ted and Laurie, who can kind of give us a bit of a context of we're heading towards the future, right, and all sorts of things. So Ted, let's take it away, mate.
Yeah, the future is now. And we're really excited about each of these weeks that we've gone through. And we've learned different ideas about designing a concept and working through this iterative design, either drawing and sketching or using 3D modeling tools. Probably the most important thing as we imagine some challenges like how might you grow crops beyond Earth or create a habitat for your family or friends on the moon or maybe on the surface of Mars, is to think about the technical challenges, to think about the biology and how it might be affected. Gil Cawthorne, one of Laurie and my colleagues, has got some really great information as a researcher. I'd like to play that video for you so you can think about how microgravity and maybe partial gravity might affect the plant. And this, as you think about your design thinking, will lead us in some further investigations. So let me share my screen, and here's a quick little video from our friend Gil. And this is just an excerpt, and so we're going to have the full video available. We'll create a link for you, and so you can see that if you go to the website as well. But here you go. Let's listen to Gil.
As I said, gravity is used by plants to orient themselves and to actually develop, right? So stems grow towards light sources, and in the absence of light, stems grow in the opposite direction of the gravity vector. So basically, if there's no light, what will happen is these plants will sense where the center of gravity is, wherever it is they're growing, and they'll start growing against it. They'll start growing in the opposite direction. So how will this change in space? So basically, we start seeing that there's different patterns of growth in space due to the lack of or the microgravity stressor that's in these environments, right? There's a study here of rice and Arabidopsis that was done by JAXA. You can see on the ground they're growing upwards and pretty uniform, whereas on the bottom you see that the growth patterns are pretty sporadic, and these kind of variations can affect the way that the plants uptake nutrients and also exchange gas. There's a lot of biological processes that can be affected by this. So the way that these plants detect the gravity in their environment is by these specialized cells. So what you're seeing here is the green ones, or the green bit there, that's symbolizing the stem of a plant, where the brown one is supposed to represent the roots. Now, all those little dots there, those are called satellites, okay? So satellites are these specialized organelles in these cells. And what happens is they're kind of like beads. So wherever these satellites pool or they collect, will actually direct a set of hormonal processes that will affect the way that the plant grows. So for example, wherever the satellites collect in the stem, if the satellites collect there, what's going to happen is that the plant is going to grow away from that. It's going to cause a gravitopic response that says, okay, the gravity is there, therefore this needs to grow upwards, okay? Whereas the roots, it's the opposite. So wherever it is that these satellites collect, the root will say, oh, wait a second, this is how to find out, this is where down is. So you can see right there, if you have a plant and it's growing just normally, and then you flip it horizontally, what will happen is all those satellites will start pulling up in that region and start directing the roots to curve down. And this will happen continually until there's a mode of stability, until that stressor is induced again. In space, these satellites don't really follow the same patterns, right? And you start getting different patterns of development in both the roots and the shoots. Now, like I said, for my research, I'm trying to develop a baseline data set of as many microgreens as I can to test with a novel growth module to be used in ground-based habitats, and hopefully eventually there. I hope that whatever it is I'm working on will be there someday, and I can point to it all the time. It's like, oh, it's there. Anyway, point is, how on earth can we test how microgravity affects plants on Earth, right? So there's these specialized devices that essentially confuse the plants. And I have one of the basic ones here next to me, which I use continually. I'm always using this in my lab. And this is called the Cozy Gravity Chamber. And it's essentially, by the way, shout out astrobotany.com. Check it out, follow us. Essentially, it's a clinostat. A clinostat is a device that continually rotates at a defined rate in order to produce a stressful environment in terms of gravity for plants. So this little device, I'm going to open it up here. Hopefully I won't trip up these wires and turn it off. In here, I have some purple Mucina that I've been doing a lot of studies with. And unfortunately, because of the glare, you can't really see the roots that well. But you are seeing, at least in the stems, you're seeing that growth is not uniform. You're seeing that even in that small chamber, where these plants are not growing all the same. Now these plants are about 3 days old. Mucina grows pretty fast. Now, what I'll do is I will take not just one, but many samples of these plants growing at different light treatments and at different speeds. And then what will happen is the roots in the entire plant will be mapped out through photographs. We'll take photographs of these plants, and then through specialized programs, we'll map out different regions, targeted regions of the root architecture, as well as the stem and the leaves. And the hope is that
now that is fantastic. If you think about it, whoops, sorry, get my video going. There we go. Gil is saying, let's confuse our statalists. Let's get our plant to think it's living beyond Earth in a microgravity or partial gravity environment. Again, the moon has got 1/6 gravity, Mars about 3/7. Lori, you've actually done some work with students and you've created something like this clinostat. Do you want to share what you've been up to? And students, we'd love to think about how you're designing something like this.
Sure. So pre-pandemic, when I was working with high school students in Florida, I got back from this conference after meeting some of the Magnitude team, and we had done this little experiment at the conference and had these little petri dishes with the Rhizobia bacteria. And it was from there that I also learned a lot about clinostats and trying to create its artificial gravity, right? It's simulated gravity. And so we can simulate microgravity depending on the rotation of the clinostat. You can simulate lunar gravity or Martian gravity. And so it's a way to ground test. And we said, well, in my classroom, I'm looking around, I don't have all the electronics like Gil did to be able to assemble. But what did I have? I had Connect sets. And so I asked my juniors and seniors in my AP Environmental class to come up with a clinostat model. So over a couple of days, they worked together in teams And it was great because this original concept was from a lab activity of building a solar-powered model of a fair ride or a theme park ride, something that had to spin. And so we took that same idea, and so this was the winning one. And Jimmy was my star engineer who designed this. And actually, he's gone on and graduated at this point and is studying engineering in college. So this was one of his little engineering projects where they took the Petri dish and they attached it to the front of the clinostat on the rotation. And then it connected to a solar panel with a wire. And that's another important element too to understand, is that there's energy limitations in space, and a lot of the rovers and satellites and even the International Space Station rely on solar power. So if you have a Connect set that's one of the solar powered ones or has the motor and electronics, you can model a clinostat with it. And it takes some iteration as well, because they had to restabilize the base. They had to realize, you know, how much mass was on the top and on the front so that it didn't tip over. So a great way to take a common tool, and even the high school students loved getting out these pieces and connecting up. I believe Ian found some other models using some other common toys and building blocks that we often have around our houses and classrooms. Ian?
Yeah, thanks, Laurie. With our conversations on these clinostats, I thought, well, how can we do this in the high school? And I know some of the students that I've been working with are really enjoying the practical side of the AVA challenge. And I looked around our storerooms, and a lot of schools have Lego sets. So I'm just going to change my camera view. So we had a look, and we had a few sets, which is called a simple machine set. We have quite a few of these, and in the simple machine set, we have, you know, your standard Lego bricks. We have a stack of gears or cogs, axles, and we typically put those together. And yeah, we might do something, you know, on simple machines as we see here. So doing some gear reductions and seeing how gears work. And I was sort of thinking, well, why can't we challenge the students, you know, using these resources to come up with making their own clinostat, which again is going through the whole iSTEM process. So we want it to be a random orientation. So we need to think about how we could do that. But also a lot of the schools that I work with also have the EV3 kits. And so with the EV3 kits, we can actually start to do some programming in there and start to use some of the sensors and some of the motors that come with those EV3 kits that we have. Jackie, if we go to the first slide that I sent through. So here's a student who's used a lot of creativity to come up with the clinostat. You can see they're just using the basic, you know, Lego components. And the really important thing is there's no one way to make a clinostat. There's a million different variations that we can do. If we can go to the second slide, please, Jackie. So the clinostat, as Gil and as Ted was saying before, it consists of a disc that rotates slowly. It can simulate the microgravity on plants, and ideally we can change the inclination, you know, using, you know, how we design it. Next one, please, Jackie. So using our EV3, there's a really simple piece of code that you can use on the clinostat. And the last one, please, Jackie, is just an example of a clinostat that's been set up using EV3. And as Laurie was saying before, a bit like a fun park ride. This one's based off a Ferris wheel, which gives kids those range of motion. So if you're after some practical activities with your kids, I know my students really like that practical activity side of things. And perhaps, you know, as a future challenge, week 7, how about you go and build yourself a clinostat? Back to you, Ted.
Thank you very much, Ian. Okay, Laurie.
Yeah, go ahead, Ted.
The challenges here, of course, are it's not true microgravity. And the plant is going through its process of growing. And as those cells divide and the plant starts to grow, it gets confused. It doesn't know which way the gravity vector is. And so if you had a piece of metal or some other material that was inanimate, it really wouldn't behave in the same way. So that's something to keep in mind as well. Lori, I interrupted you, so why don't you go ahead and talk more about either about the Kleinstedt or about the future, right? I know that's pretty exciting. Where is all this going, right?
Absolutely. So I had to add my virtual background here because this is where we are going. We are going to the moon. And I have just a few slides that I want to show you. And so let me share my screen. So research is taking place on the International Space Station. Over 3,000 experiments. We've had our ExoLab experiment up several times. And the plant team at Kennedy Space Center and really around the world has been working diligently in growing microgreens and different lettuce types and radishes. And most recently, they've been growing space chili peppers. Maybe you've heard about that. So the International Space Station, one of the plant devices that they use on the station to grow is the Advanced Plant Habitat. And this is the little mission patch that was for the Hatched ISS Space Chili Challenge. And that is what the Advanced Habitat, Plant Habitat looks like. So it is a growth chamber that has sensors and cameras, and they're able to really closely monitor the health of the plants. And that is the chili peppers growing in there. And this is connected to a citizen science project that was led by one of the KSC engineers, Jacob Torres, who is from New Mexico. And he got citizen scientists of all ages involved around the world doing ground trials, testing out growing these chili peppers, who could grow the spiciest chili. Well, the astronauts took that information. Jacob and the plant team at KSC built on that information collected from all of the ground trials around the world, and they ended up making space tacos. And there they harvested the chili peppers. This was the Crew 2, Dragon Crew 2 that just returned a couple days ago, and they got the joy and privilege. I mean, you can just see the smile on their faces. They were ecstatic to be able to grow chili peppers in space for the very first time. And Megan MacArthur, she had this idea to have space tacos. And if you're familiar back from, maybe the 1980s with the California raisins lineup, we're now going to replace that with the space chili peppers. But you can see how well they did in the Advanced Plant Habitat. And that was leading up to so many ground trials. And then being able to harvest and test both the green chilies and the red chilies. So it was a pretty small volume of space, and they got a lot of peppers. You can see all of those flowers in there. And either they had to be tapped or a fan would circulate so that the flowers would move, and then they would self-pollinate. And so that's one of the technologies that they use currently on the International Space Station to grow plants. And I'm going to pause this slideshow because I want you to hear from Megan MacArthur about their reaction to tasting the chili peppers.
Thank you. Next question from Sean Griswold with Source, New Mexico.
Hey, thank you so very much. I'm calling from the land of green chili in New Mexico, and we all thank you for introducing chili to space. Thank you very much. And I know that you tried to figure out how to roast the green chili, which activates the flavor and spice. Can you discuss that process, and was it successful? Did you roast green chili in space, or were those tacos with raw green chilies? And I'm curious to know if you all wouldn't mind telling me how those tacos tasted, and was it the green chili that broke the toilet?
Well, those are a lot of interesting questions. So yes, we've all been very excited about this Plant Habitat 4 project that's been ongoing for over 100 days when Shane initiated the project by planting the seeds, and that it has been run from scientists on the ground for these several months. And so it's been a really nice ongoing experiment for us. We can come and check on the plants, and then occasionally when someone would get inside the habitat, we could come and smell the plants and see the chilies growing. So it's really been a nice morale boost as well as an interesting science project. So we were all very much looking forward to the harvest. Mark harvested the first chilies last weekend, and we all got to taste them. And I think we were a little bit too excited to go ahead and taste them, so we did not take any time to roast them. We only have a warming oven on board that goes to about 180 degrees Fahrenheit, so we could make them warm, but we couldn't really roast them. So we elected to just eat them raw. We all tasted them, both the red and the green, and they have a nice spiciness to them, nice little bit of a lingering burn. Some found that more troublesome than others, but we did all enjoy them, and the tacos were very tasty. It's really nice to have something that smells so fresh and then has the nice crunch of a fresh vegetable as well. So it was a real treat for us, and obviously something that we talk about and think about quite a lot. Thanks for the question.
Thanks for that, Megan. That was great.
So one of the reasons chili peppers were chosen is because they're very high in vitamin C, and that is a nutrient that tends to break down in the prepackaged foods. And so as the plant team is selecting crops, they're looking for high levels of certain vitamins and nutrients that will help support the health of the astronauts. Vitamin C, vitamin K, the B vitamins. And so they're identifying the plants that will best grow in the space station in a closed environment, and then also that will help the astronauts, that they'll enjoy it, that crunch, that flavor, that taste, that spice. Because of the fluid shifts, you can even see in their faces that they're a little bit, it's called chicken legs and puffy face. And that's because of the fluid shifts in their body. And so that tends to interfere with their senses of taste and smell. And so by having something that's spicy, it makes the food taste more flavorful than what they're used to. And so that was a tremendous goal reached for the first time to grow these. And where are we going? As we talked about earlier in the AVA weeks, we're going to continue in low Earth orbit as commercial partners build additional private commercial space stations. Just imagine growing the plants and the different technologies that's going to be required, from hydroponics, in situ resources, as well as aeroponics is being explored in some technology. So you can see that plants are going to be an integral part of establishing our low Earth orbit economy, as well as then taking us to the moon.
That's right. And it's not just happening like in the far future. This is happening this decade, just in the next few years.
50 years
ago. And I'll just end with this.
We went to the moon. We called it Apollo.
What many people don't know is that Apollo had a twin.
She was a woman named Artemis,
goddess of the moon.
We are returning to the moon
as a new generation of explorers.
This time to stay.
And to prepare to achieve humanity's next giant leap of sending the first human missions to Mars.
We believe our course will redefine what is possible.
That we would discover life-saving,
earth-changing science.
And that the challenges ahead will inspire generations.
This is our manifest.
For all who wondered if we could return.
For all who dreamed of pressing beyond.
This is your calling.
We go for all of America.
We go.
We go
as the Artemis generation.
We go.
So we are going back to the moon, and there's so many different ways that you can be involved in getting us there and for us to stay there and live sustainably. So I challenge you with that and commend you as you have worked these last few weeks and contemplating how to grow plants and how we can survive in future settlements on the moon and on Mars. Ted?
Lori, that's fabulous, Lori. You know, as we think about something like the clinostat, something that rotates, the planets rotate, they rotate, you know, around the sun. You know, I guess I want to, seems a little bit of a stretch, but I want to bring Jim in because Buzz Aldrin actually had an idea about how to deliver food and supplies and people in a more effective way between Earth and Mars. So Jim, do you want to talk a little bit about that that model that Buzz had come up with, and also the Home on the Moon challenge, what you've been doing there?
Yeah, very excited about that, Ted and Lori. What a great presentation. The videos were so cool. First, I just like to say, I spend my time trying to figure out how to make these ideas understandable and think about ways to express these kinds of things to students. And I just really have a good time with this. When Ted gets started talking about the Aldrin Cycler, I want to talk about that a couple minutes, but what I'd like to start with is a project that we got started just about pandemic time. And what it was we called it Home on the Moon. And the idea was that I had been traveling a lot, and one day I'm sitting and I can't go anyplace. And I thought, I might as well be on the moon. And I realized, if you're going to be on the moon, you need air, water, food, shelter, energy. The same thing you need if you're living in Sydney, Australia, or Orlando, Florida. Air, water, food, shelter, and energy is what you have to have. So I began to think, how do I get those things at home? And there's a system for every one of those things that we have in your home. And you've got an HVAC system, you've got plumbing, you've got electrical system. We were hiring somebody to bring food into us at our house. We were really hermits. The shelter, exactly what do we need? And I begin to think, how much do we actually use? And how do the systems work? And then I begin to think, how would these systems have to change if we were going to put them on the moon? And I started playing with all of these ideas. As I started playing with these ideas, I came up with this idea of a project where I'd ask students to design their homes on the moon. But first, they would understand how their systems all work, something that I think most people don't. The next thing is that they would collect data and look at exactly what it is that they use. And then once they'd done that, then they'd start considering, how would the system have to change on the moon? Now, of course, when we went to the moon the first time, and when we return with Artemis, it's kind of a camping trip. We pretty much take everything we need, but when we actually set up camp and we're going to stay, we're going to want to be recycling things. And it's going to be a case where you're not going to recycle everything, and it's not going to be a perfect system. But I set up some rules of what you could expect. How often are you going to be resupplied? What can you get? Where is it coming from? That type of thing. And we were asking students, figure out how you could recycle and reuse most efficiently. Also, we told kids that you could anticipate that we would build your house using some type of a 3D printer that would be operated off of using lunar regolith as the source material. But we set up this entire thing. Then the last thing we did was, and this is what really gets me to the Aldrin Cycler, is we started looking at, okay, why would we be going? And we set up what we called a backstory. And the backstory basically said, we went to the moon in the 60s and the 70s. We pretty much ignored it until about 2020, and now we're going back. And I wrote it as if it had already happened. The first woman's been on the moon, women are on the moon, men are on the moon. We're up there. We've got an orbiting station. We have the Collins orbiting gateway, I call it. We've got a science station on the North Pole that we named after Neil Armstrong. We've got a logistics station on the South Pole that we named after Buzz Aldrin. Can't forget that name, Buzz Aldrin. And then we're to the place where people are starting to come up and being tourists. And the worry that we have is somebody going to go up as a tourist and kick dirt into the footprints? And so what we wanted to do was ask kids to build their homes at the sites of Apollo landing sites, such that they could protect and defend those sites, maintain those sites. Now, wrote out this story, and we started asking people to do this, and we put together a lot of resources, and it's on our Aldrin Family Foundation website. Now, when you go to Aldrin Family Foundation, you're also going to find out about giant Moon and Mars maps, but that's another day. But you can go through this project. Okay, so I kept extending this out. Now, I don't know what the future is going to be, but I'm inclined to think that the future might be a lot like the past has been. And the past, we have explored and gone places ultimately because we could make money doing it. And I begin to think, how are you going to make money on the moon? And I look at it and I think it's because of resources on the moon. I think once we can get to the moon and we can actually be living up there and doing things, we can start mining the moon. Interesting thing about the moon is it's 1/6 gravity. We can throw things off the moon. We don't have to get them very fast to get them into orbit. If you can throw ore into orbit, and if you could build an orbiting station to process this ore, you could process aluminum, iron, all kinds of things. You could process water into hydrogen and oxygen and drinking water. You could have the materials you need to build a rocket and the fuel to fire it up with. If you could do that going around the moon, you could build it such that you could have constant solar power. And if you can build things in orbit, in microgravity, you can build huge structures. Okay, Aldrin Cycler. The idea of the Aldrin Cycler is to build a spacecraft that you can put into orbit around the sun at a speed, at an orbit, at a trajectory that intersects the Earth and intersects Mars, and then about 26 months later is back to the Earth, and then sometime later it's out to Mars, and 26 months later. And anyway, it's a 26-month orbit intersecting Moon, Earth, and then Mars, and just continuous. And you don't have to put any energy into that to maintain that. Now, if you were to build a second one, you could set it up to intersect Mars and then Earth every 26 months. You could have inbound and outbound. And so the challenge was I asked students, design what something like this would look like outside of the restriction of building it such that it has to be launched from Earth. You could build something big with materials from the moon. Okay, so that's a thing that I've been messing with quite a little bit. And if you're interested in doing these kinds of things, we've got this on our website at aldrinfoundation.org. Now, I think at this point, Ben, how about if I kick this back to you?
Mate, so appreciative of your time, Jim, absolutely. And as well as Ted and Laurie, thank you so much. These are big ideas, aren't they? They really are. They're so cool. And what I think about, especially with that video that Laurie shared with NASA, we're going to the moon. Isn't that about story? It's about communicating a message to make sure your audience gets engaged. And actually, I don't know about you, but you kind of get a bit of, I got a bit of goosebumps watching it. And so I kind of think of, well, Carey is coming up, and Carey really helps us with knowing about how to communicate using story, how to communicate your messages in a way that audiences are receptive. Because let's be honest, you're doing a 1-minute pitch as part of this design challenge for the Australian Virtual Astronaut Challenge, and you got to document it, right? So Carey, I was wondering if you guide us through a little bit of your world.
Okay, so let's share my screen here. So hopefully you can see that. Wow, my mind is totally blown at the moment. So this is just amazing and so exciting what is going on in the world, and how exciting to be a part of it. So communication and the challenge of collaboration. So communication is a really big concept, and communication can be speaking information, or it can be writing or documenting information. And it becomes even more complicated if you need to speak and write in collaboration with others. So it is actually so difficult that most companies say that when they hire staff nowadays, that communication skills are at the top of their list. And this is because it doesn't matter how clever you are. It doesn't matter what your qualifications are. If you cannot communicate your ideas and collaborate well with others, then you will have very limited success. So, and that's not just in your work life, that's in your life across the board in every aspect. So, can you imagine being an astronaut in your spaceship with other astronauts for a 2-year mission, and one person is taking over the communication. You know, they don't listen to anybody else's ideas. They talk over everyone. They mess up other people's work. And that would be such a difficult situation to work and live in. And it's dangerous too, because you can't get out of the spaceship. So when you collaborate, you have to listen to other people's ideas and questions. Their knowledge needs to be added to yours. And together you can build knowledge and solutions to all sorts of problems, even ones that you may not have initially thought about. So we've included a question slide here. It's in your AHA. You can let us know what challenges you've had with collaborating and documenting your collaborations. So you can access that in your AHA, and it will remain available to answer at any time. So you can fill that out now or later. And if you're watching the recording, you can answer that at any time. So a very important part of doing science and being scientific is documenting your questions, answers, and process. Whether you use a pen and paper to jot down ideas, or you record them on your smartphone, or you're writing into a Word or Google Docs, you need to make sure that you're documenting your questions, answers, and the process you went through. So when you're collaborating with others on documents, make sure you're not deleting somebody else's work and it's lost. You know, you need to think about, how are you filing and saving your information? Do you have a good system for that? And how do you share and showcase your work? So I'll unshare my screen and we can show you the folio pages there. And so let me just stop sharing there. So Jackie can show the folio pages. You've got instructions on how you can use Instagram, how you can do a podcast, and it's on pages 63 through to 66. And teachers also have an option to use my FamilyBookform technology, where you can collect students' content into automatically formatted published books. And so this would be ideal for maybe the end of the project, so you can collect students' finished reflections on the whole experience, and maybe their analysis of what they learned throughout the whole project. And you can let us know if you're interested in that. So we're going to jump to Dr. Sleap now to discuss your pitch presentations. Thank you, everyone.
Yes, thanks, Carey. And like, communication is just so important in what we're doing. So we've been doing a lot of written communication, and I agree. What a great thing to potentially do is to create a book about what you've done and your experiences through the work with Carey. But what I'm going to talk to you today about is pitching, because that's what we're leading up to, and is the main outcome of how we're going to communicate all the work we've done. And we've got 1 minute to do that. So that is very difficult. It's actually very easy to do a pitch, but it's difficult to do a really good pitch. And I'm going to give you some tips and hints. But first of all, what is a pitch? Basically, it's like telling a story. It's a concise way of doing that. And it's about like why someone, in a marketing sense, if you're being entrepreneurial, why they would buy your product. But in this particular case, it's why Ted would consider your idea, or why NASA through the Artemis program might decide to use your work. So we often do that using a pitch deck. So I'll get Jackie to put up on the screen the notes. So on the right-hand side there, you'll see the information about a pitch deck. So a pitch deck is a way of basically just having some slides in the background to help you on your way. Now, different types of pitches will use this pitch deck and some won't. So you don't have to use a pitch deck. For instance, the different types of pitches there are, the main one which uses a pitch deck would go for about 3 to 5 minutes. Okay, you've only got 1 minute. So the type of pitch we're kind of talking about here is like an elevator pitch. So an elevator pitch is just like really short and concise, and it's usually quite verbal. The other type of pitches, which I love, is like a napkin pitch, where you're sort of just drawing on a piece of paper what your ideas might be. So I just want to talk to you a little bit about like some common mistakes. So the common mistakes in pitching, the most common one is taking too much time. You've got to make it concise. So that's why we made the decision to do more of an elevator pitch rather than a full pitch in this case. Now, again, pitching is about telling a story. So poor pitches don't do that. So the person or the audience wants to know your story, and they want to get that in a narrative. Now, a good way of actually highlighting your narrative or your story is using a picture, a graphic or a picture, or some sort of prop. So it could be your prototype. Now, a good way of doing that is showing that during your presentations, or it could be within your pitch deck. Now, another big problem is not recognizing what the problem is. Now, you need to articulate and explain to your audience what you're trying to solve. So what does your particular item solve? Okay, so be thinking about that and identifying the opportunity. So why is yours unique is quite important. So in the structure of your pitch, if you're doing a 3 to 5 minute pitch, you'd use 8 to 10 slides. For this, because you're doing 1 minute, you'd have a lot less. So within that, you need to sort of look at the structure, and in here gives you some hints of how you might structure that. So first of all, starting with a story, identifying that problem and do it as a narrative. Then identify your solution, and again, really pitching into why yours is unique, why yours is special, okay? Outline the potential of your idea, like what it could achieve. Now, in the ask section, the ask is normally in a pitch going to an investor and saying, I want $20 million to produce this item. The ask for this particular one would be going to Ted and saying, and explaining why you would use your product, your experiment, your design in this particular task. Now, also in this, you should be highlighting your team. So, and this is where your opportunity to get your pick. So why can your team and your design be the best? Okay. So some other things to be aware of: know your audience, keep your language simple, but really powerful, be confident. And like what I'm doing at the moment, probably speaking a little bit too fast. But the most important thing too is be passionate. That these are your ideas. So get that passion out there about why you think your project is so good. And one thing I just a couple of things I'll finish up on. The word pitch, okay, it comes from the idea of pitching a ball. Now, if you think about what that means, is you've got a pitcher who is throwing this and is trying to get that to the catcher so that the batsman doesn't hit it, okay? Now, they have to communicate to each other without using verbal means. So non-verbal communication is extremely important, not only in pitching, but in doing a pitch like we're doing. So some of the things that you need to be aware of in those non-verbal areas is like your tone of your voice, your appearance, eye contact, being confident, using gestures, showing props or graphical information. So be aware of that. So just to finish off on this slide, below I'll put some 1 minute examples of pitches. These ones don't have a pitch deck. They are just people talking. So, but they'll give you a really good understanding. These are all award-winning pitches. So and it's worthwhile to have a look at that before you do your pitch. And if you just scroll down to the activity section for me, Jackie, in the next page, there's a little task that you can do to help you to organise your pitch as a group. So I've just put a couple of blocks there. So they would represent a pitch deck. So this is a storyboard. So put your ideas about what you would do in each of those, either as a slide or the natural segmentation of your pitch of how it will go in sequential order. In the bottom section is just some ideas about writing down like you're going to use props. So you're going to have a presentation, who's going to say what at what time, and like if there's other things that you need in terms of your non-verbal communication. So that's me. I'm now going to hand over to Wendy, who's going to discuss again about where we're up to with our folios. Over to you, Wendy.
Thanks very much, Scott. Before we go into our folios, let's just recap the entire challenge. So in these 6 weeks that we've just had, you completed activities as if you were actual real astronauts on a mission. And you used the design thinking process to develop a new plant growth mission for the International Space Station or the Moon. So how are we going to get to the end and how are we going to finish off our pitch? Well, let's just have a look at what we had last week in our folio, because last week Ian and I talked to you about how to evaluate your project using the plus, minus and interesting factors of your design. You then had the opportunity to refine your design or your concept, and also in your portfolio, we didn't go through it, but you find there's information on how to create a cardboard dome. And I finished with a little segment on agility training in our Train Like an Astronaut section. So now I'm going to pass over to Ian so he can go through this week's folio, and then I will end on our last Train Like an Astronaut concept.
Okay, thanks, Wendy. Jackie, can we throw up the slide that has the ISTEM process? So the ISTEM process, we looked at this way back in week 1. This was page 4 of our very first folio. And over the last 6 weeks, we've been working our way through each of those cogs from define right at the start to today, we're at the communicate stage right at the end. I do want to point out that we also have 2 other of the ISTEM engineering design process cog setups as we see there. We do have one which is a 5 cog system, and that's aimed at kids in early stage 1. And we also have a 7 cog system, which is aimed at kids in stages 1 to 3. The one that we see here is aimed more at our secondary kids or our upper stage 3 kids. Jackie, if we can go to the next page on the folio, page 59. And page 59, we're looking at communication. And we're looking at the fact that we need to present our drawings. So we want page 59 of this week's folio. And one of the things that we're asking you to do this week is to prepare your drawings. So prepare what we call orthogonal drawings. So orthogonal drawings is we take our pictorial drawing that we've maybe done either using pen and paper methods, using the splat tool as Glenn showed, or perhaps using one of the computer aided programs that we looked at the last few weeks. So we looked at Tinkercad, we also looked at Google SketchUp, and we mentioned quite a few other ones. What we want to do now is we need to get that detail out. So if we're going to build something, we need to be able to communicate that to manufacturers. And so what we need there is what we call orthogonal drawings. And orthogonal drawings give us a top view, a front view, and usually a side view. They give us measurements, and we draw those to scale. If you look on the page there, page 59 down the bottom, you will see those 2 red sort of movie camera icons. If you download the PDF and you click on those, that'll take you to a video link that will show Glennie D demonstrating how he drew that jiggler device, as well as how he drew the ExoLab, which I had some students looking at yesterday, and it was really engaging for them. What I want to do just to finish off with today is if I can share my screen, and I'm going to show you just in, I'm going to go back to what we did a few weeks ago, and I was in Google SketchUp. And when we were in Google SketchUp a few weeks ago, I showed you how to draw the 5 basic shapes that Glenn introduced the week prior. And so what I've done here, I've just drawn a really simple block. And what I'm going to do is show you another feature inside Google SketchUp, which you may or may not be aware of. First thing I'm going to do is just highlight the block, and I have already saved it. This is an important step that you need to do. But inside Google SketchUp, under the File menu, there is a command that says send to layout. So if you send that image to layout, what you'll find is you'll come in with an object like this. Now, there was a screen prior to this, but I'm just trying to speed things up for today's presentation. So the screen before asked me what size paper I wanted to send the object to. So I chose an A3 piece of paper, and I also chose to have an A3 piece of paper which had a title block down the bottom, which you can edit. So I've got my object in there. This is my pictorial, which I drew really quickly and really easily. What I'm going to do now is I'm going to copy that image, and I'm going to paste the image. It pastes right on top of where the current image is. So I'm now going to slide my copied image across to the left, as you can see there. And in Australia, we use what's called third angle projection. So third angle projection, the top of my page will be the plan or the top view. And over in SketchUp over here, you'll see here it says camera standard view, and it says none. I'm going to change that to top view. And as soon as I do that, my block that I've drawn has now, the computer has automatically generated my top view for me. So just to show that again really quickly, so I'll copy that image again and paste it. And just to give you an idea, I'll bring this one down here now, and I'll make that one a front view. And that's generated for me as well. And I can line these up because in my orthogonal drawings, my top view and my front view need to be directly above and below each other. And likewise, if I want to do my side view, then I can do the same thing, bring that one down, and I can make that a right side view is what I would like there. The last thing we talked about was some dimensions. So in Google SketchUp, in the layout, there is a really simple dimension tool. So again, Google SketchUp is pretty smart. It knows how to click onto ends, etc. So that's 100. If I come across here, I've got my sizes there that I need. And if I want to add some detail to my drawing, I can do a label. So I might have a label. I might point to some part of the object and come across here and say, the bottom, right corner. The details I want to put into there. So I just wanted to show you guys that today. So if you're doing it electronically, you can save a lot of time doing your orthogonal drawings by using the center layout tool inside SketchUp. And I'll now pass back over to Wendy.
Oh, thank you very much, Ian. You always give us such great information on these drawings and using online tools. Now, training like an astronaut is so important to the astronaut's health and well-being. You can't just go out into space and not actually look after your body, because you need to be doing massive missions as well. So we're going to look today at body weight squats, and they are explained to you on page 67. Now, I've done quite a few of these in my lifetimes. You can even add weights if you want to make it more difficult. But today's body weight squats is all about strength training. And also push-ups. If you're really good at push-ups, you can do really hard ones on your hands and your toes. Now, before I finish off, I just want to remind teachers and students as well that on our website, you will find a link to a post survey. We would really love for you to finish that post survey for us once you've finished the course, so we can find out what your thoughts are. Over to you, Ben.
That is so cool. And look, actually, we've been getting lots and lots of feedback from the AHA slides with different ideas about the challenges with collaboration and what on earth they might do on the moon. Isn't that interesting? So one challenge I did notice was when you have a mind block and can't think of any ideas. I get that. I totally do. Best thing, sometimes it's just better to just walk away for a moment, do something completely different, and then come back. Maybe have a chat with your team. Do you know that as artificial intelligence grows, as AI grows, people are using that to actually start themselves on a bit of a path towards creating stories, helping them break mind blocks. Absolutely, for sure. Now, I do also like that there was another one came up, which was agreeing on ideas and incorporating all members of the group into the project. I want to give you a heads up. Friction is actually a good thing, because it means that dynamic sort of feedback between each other means that you can, hopefully produce something better. Being all in agreement may not necessarily mean you're going to have the best product at the end. So don't worry if you're having agreement issues. Just make sure that you all have a common purpose, a goal to reach, and you'll be fine. Now, guys, I thought that the panel has been reading away some of the other ones. Some really interesting ones came up, especially with some of the activities on the moon, especially, Jim, baseball was a little bit interesting.
Yes. Okay. I'm back. Yes, I spent a lot of time thinking about games on the moon because gravitational acceleration is 1.62 meters per second squared, as opposed to on the Earth, 9.8 meters per second squared. So not only do things weigh 1/6 as much, they fall 1/6 as fast. It'd be like falling in slow motion. When somebody throws something to me, I judge how fast it's coming by how much arc there is. The arc is going to be flatter. I think it would be really interesting to consider how that 1.62 meters per second squared acceleration affects our games.
I love it. When you think about games, really it's applied physics, right? It's the balls are moving around at certain motions and certain force. And hey, if you want to score a goal or get someone out, you need to know how that's working on another celestial body. I love that, Jim. That's awesome. And one that also grabbed my attention too is Lily from MacArthur Anglican would love to explore surroundings on the planet and maybe eat some space food. So I'm thinking space tacos, Jim.
Yeah, absolutely. You know, there was comment about that. I think Lori said about seeing the joy in their faces. I want to see the tears in their eyes from the heat of the pepper. That's what I want to see.
Oh, that's yeah, I totally get that. And so Jesse from Sacred Heart wanted to play baseball. And by the way, Finley from Tahuna wanted to play tennis. How on earth would tennis work on the moon?
Well, I'm really curious about that as well too, because again, the arc is what you're going to have to be doing is you're going to have to hit the ball down. You're going to have to, I'm guessing you probably make the net a little bit lower and you're going to hit the ball down into the other court. It's what I would guess.
Would that be cheating, changing the rules, or is that just how it's going to be?
I think when you take a game that was designed for Earth gravity and you try to place it someplace else, I think it's inevitable that will change both what the field, what is it, the pitch, what the court would look like, and what the equipment would be like, and some of the rules. I think it's inevitable.
All right,
I'm with you, Jim.
Yeah,
I was just saying, imagine the tennis court might be 6 times larger there, Ben.
Well, okay, so what's crossing my mind is what on earth happens, or what on moon happens. There's not concept. What about the Olympics? How does that work with the moon team versus a terrestrial team? I mean, how does that work? Who knows?
Well, I've been, and I think Ted wants to jump on this one, but I've been thinking about, do you run faster or are you slower on the moon? Because every time you jump, every time you go off the surface, it's like slow motion up and down, but you can still push yourself laterally quickly. So you can take these long steps.
I volunteer to test that. I'll do the first marathon on the moon.
Space runner, absolutely.
Absolutely, that's me. I'm a space runner.
Would it be 96 miles? Wait a minute, is that 6 times?
No, well, 26.2 on Earth. We'll have to come up with an equivalent on the moon. Though the spacesuit may be a little more limiting because right now it's kind of more of a bunny hop than it is a run. So.
And that regolith, right?
That regolith.
Right. It's not on a nice.
I reckon
nice
that
asphalt.
we could totally riff on this for quite a while, but I do know some students do need to run on to their other classes. So thanks so much on that, Ben, and thank you everyone for submitting these things on the slides. Now I'm going to do a bit of housekeeping. Sorry guys, have to do a bit of housekeeping. The final date for submissions, because there is a submission. You're doing a 1-minute pitch. You're using the communication tools that Carey and Scott mentioned, and all the things you've been learning throughout the 6 weeks to produce something that we can sort of see, what Ted and Laurie can see. How might we grow food in space, which is eventually what this is all about, right? So final date for submissions for phase 1. Guess what? There's 2 phases. That's how it's going to be. But Monday, 22nd of November, that is phase 1 submissions. Now, don't stress if you haven't started this particular process, because we know people are incorporating in their scope and sequence in all sorts of ways. So we're also going to have several weeks after the fact as well. So if you need to have more time, that is not trouble at all. I know that Dr. Sleap has sent across where to send your submissions. Please send them when you have the chance to. Now, I do also want to recommend too, don't forget the Australian Space Biology Summit, that link that got sent earlier on. And teachers, please check your email. You'll have that link. What you're producing for the Australian Virtual Astronaut Challenge, 100% can be used for, well, the ASBX challenge. So look at asbx.com.au and you'll find this out. Now, by the way, there's a prize. Why not? Let's have some prizes. There are some to be announced, but one of them will be the prize for the 5 awesome schools. Let's be honest, you're all going to do awesome stuff. Yeah. But the 5 schools that Ted and Laurie and Jim go, you know what? These are really cool submissions. Physics education will be running a liquid nitrogen / space show, which will be kind of fun, bit of what we actually do when we do science outreach, and we want to kind of celebrate. And that will be kind of fun as well. That dates will be announced. We've got to sort that out later. Now, thank you so much, everyone, for being involved with this particular challenge. And we've got everyone now on screen, sort of up there. So look, much appreciated. And enjoy week 6 as you produce your 1-minute pitch videos. Enjoy your day, guys. Have a fantastic time. Unfortunately, like always, these things self-destruct. It's going to. So much appreciated. Thanks for Peter and Jackie from the physics team for making this all happen. This is going to self-destruct in 5, 4, 3, 2, 1. Have a fantastic time, guys. All the best.